Hi, everyone. Thank you for having me. And huge thanks to JetBrains for making this happen. I'll jump right in because we have a lot of ground to cover. Logging is essential, whether it's a development environment, a staging, or production one. Distributed systems have become more popular than ever for a number of reasons, and the same stands basically for cloud usage. There are numerous ways of writing and reading logs, endless combinations to use. Someone could also use console write line and start looking at the logs from inside the container. But in this talk, I'll show you a balance between usability and cost for logging. So without further ado, let's move on and see the agenda. We'll examine the cost and usability of our solution, which is the OpenTelemetry collector, Loki, Grafana, login pipeline, compared to CloudWatch and OpenSearch. We'll do an initial setup in AWS and configure the Elastic file system to be used with Loki. We'll examine different approaches for persisting logs through Loki. Next, we're going to deploy our login pipeline to AWS using ECS Fargate tasks. We'll set up a .NET API to write logs to our login system. And finally, we'll have a brief look at tracing and metrics for a full observability suite. There will be some things throughout this talk that are not being used at this point in time. Maybe there are older ways of doing stuff. They are in here just for reference so that you know in case you come across a blog post or an article regarding logging with these technologies, in order to know what you're seeing and to understand whether you should use it or not. So let's go on to our first section, examine the cost and usability of our solution compared to CloudWatch and with or without OpenSearch. Okay, we need to think what is the question we're trying to answer here. Why are we using this open source approach instead of relying on the native services for logging that AWS provides? There are two established native approaches to logging in AWS, CloudWatch and OpenSearch. CloudWatch is relatively inexpensive for storage. Its ingesters are the ones that charge the most, but querying logs can get costly. The reason being that CloudWatch login sites cost adds up quickly with frequent searches. Logs are separated into groups and streams, which makes searching difficult compared to Loki or OpenSearch. Log groups are run per application, and streams are run per instance, but that's not always the case, because if a container restart happens, it will create a new stream. Also, regarding CloudWatch, it also kind of forces you to use it when running Fargate tasks, but we'll see more about this later in the session. This is a screenshot of some events streams in CloudWatch. It can be pretty cumbersome to find logs in here, even though you can use a search. I'll move on to the next slide that has to do with OpenSearch, which is an approach with greater potential. It is built using Elasticsearch, and retrieving logs is fast, while also supporting complicated queries for searching. It has two options, the managed and serverless one. The first one being generally cheaper, and the second one being preferred for simplicity and rapid scaling. We'll use a cheaper of the two options for our comparison. The main downside is that OpenSearch, for native AWS integration, requires CloudWatch subscription filters. These filters stream logs to OpenSearch either via Lambda functions or Kinesis data firehose. So we can think of it like this. Subscription filter is the trigger, Lambdas do the JSON formatting, and then OpenSearch creates the indexing. Natively is the key here in our comparison, as someone could build a custom solution around it by using OpenTelemetry, for example, having an OpenTelemetry corrector, sending data after transforming them to the OpenSearch. So Kinesis Firefox is generally cheaper of the two, but they are both approaches are considered expensive. OpenSearch also requires EC2 instances for data and master nodes, and EBS storage for indexes and replicas. These costs are ongoing, even when log ingestion or query activity is low. So even without high volumes, when dealing with high log event frequency with small log size, to give you an example, this can be constant writes from background service. OpenSearch combination of subscription filter costs and infrastructure costs can easily be more than 3 times more expensive than the OpenTelemetry collector with Loki and Grafana solution running on ECS Fargate. The latter is also cloud provider independent. It provides full control over log retention and query performance. And we can make it even better by adding traces and metrics for a full observability suite, all visible through Grafana. Now, a few more words have to do with this comparison. OpenSearch indexes content of logs, not just labels like Loki does. We'll go more in depth for this. Basically, we want to know what labels are for Loki. To give you an example, it could be the service name, but we generally can have labels that we have declared in our application or in our OpenTelemetry collector. But Loki index is just that, not the whole content. Let's move on to the next section. And let's start implementing our solution. We need to deal with some policies and configurations now, so we don't run into issues later in the process. They are quite a lot, but they are necessary. So we create the EFS from the AWS console, then we go straight to IAM to create the policy. We name the policy EFS policy, or however you like. We change the user ID that you can see in the screenshot. Is the one ending in 798. And the region, of course, if you're using in another region. And also change the EFS ID, and we are ready to go with this policy. Now we'll create the role to handle the task execution in ECS Fargate. We'll name the role ECS task execution role, or again, however you like, and we'll add the policies shown in the screenshot. There are policies here that are not needed for a specific task. For example, there's an RDS policy for the OpenTelemetry collector task, but this is a general role that should cover the functionality of other tasks as well. For example, a .NET API, not just the tasks related to the login. We need to also make sure that we include the EFS policy that we created earlier. And let's go ahead and create another policy, the custom EFS policy this time. Again, we change the user and the EFS ID, and basically we use the EFS IAM permissions, client mount, describe targets. Well, we need them for mounting the EFS on EC2. We move on. We'll create the EC2 instance role, and we'll add the policy we just created to this role. The role will be used later when we create an EC2 instance and mount the EFS on it. So that's pretty simple as well. Now, we'll go on and create the EC2. During the creation process, we'll need to create a key pair certificate. We'll use this to SSH later into the EC2 and create directories. Also, attach the EC2 instance role that we created earlier during the EC2 creation. We'll use the same security group across our services in the VPC for simplicity purposes. Now, we open the terminal. I'm using Mac, it's using ZSH, and we go to the directory where the certificate is saved, and we run this command, chmod 400, the certificate name, get rid of permissions. Then we move on to the AWS console, and we go to the security groups, and we add this entry for SSH port 22 for the source 0.0.0.0/0, which means basically that we allow our service to communicate. We will allow communication to the EC2 instance from anywhere. And we also have the other entry that mentions as a source our security group, which allows the communication throughout the security group for all our applications. Again, this is done for simplicity only. I mean, this is not for to use for production. Then we'll SSH with the last command into the EC2 instance by using its public IP and the certificate we have created. Okay, so once connected to this instance, we will need to mount EFS to the /mnt/cfs directory and create the folders that Loki will use. So the first command mounts VFS to this directory on EC2. We create the other directories, rules, chunks, wall, index, BoldDB cache or TSDB cache. It depends on the storage option we have selected for Loki. TSDB cache is the newer one. Compactor, and then we have the last two commands that have to do with the owner, basically, of the directory. So we say that the owner, which is at this point is 10,001, can read, write, and enter all directories, and other users can read and traverse but not modify. The reason we're using this specific user ID is that it's the default user ID that Loki uses if we don't specify anything else when the Loki container runs. And in order to ensure that the EFS is mounted, we run the last command as well. Let's move on. We go to the ECR from the AWS console. We name our repositories however we like, and then we'll go on to push our images to them. If I'm going a bit fast, it's because I want to have time to explain everything. We'll now examine a few different ways that we can persist our logs when using Loki so that we can have a better understanding of the options available. So the first storage option is the BoldDB shipper with EFS, the V11 storage schema. It stores indexes, chunks, and WAL. WAL is the write-ahead logs on a shared file system, such as EFS. Here the ingester sends logs to WAL and EFS for durability and sends the indexes and chunks also to EFS. In this setup, nothing's been shipped to object storage like S3. The pros are that it's easy to set up, it doesn't depend on S3 as it uses one place to store everything, and the process itself is simpler as there is no shipping or compaction take place. The cons are that it has poor scalability due to EFS that makes queries slower with larger volumes. It can be quite expensive, that's a lot of data, or high query rates, and there's no structured metadata support. Basically, it's being used for testing and development, so we avoid the costs, and because we don't need the scalability. Now, regarding the fact that there's no compaction, the compactor is only relevant when you're merging small index files in object storage. With EFS, Loki just keeps writing new BoltDB files. They're not compacted. Now, if Loki had structured metadata support with this storage option, like we'll see later in the TSDB schema, the main way to benefit would be by using structured logging. So in the case of unstructured metadata, like this, we have raw text, no key value pairs that is only searchable with regex full text search. Loki cannot understand structured fields, although it has labels for resource attributes. In the case of structured metadata that are supported in version 13 that we'll see later, we have key value pairs that are stored alongside log entries. Loki can understand structured fields with version 13 schema. For example, an entry can be that the service equals order, the user equals Alice, and the items are 3. Since Loki understands structured fields if we had structured metadata, we could have a query to show all purchases where items are greater than 2. We'll talk about structured metadata later as well, so let's move on to the next option. Storage option for Loki is a BoltDB shipper with EFS and S3 this time, so the persistence will happen in S3. It uses 3 for long-term storage of chunks and index files, while EFS provides persistence for the WAL and temporary chunk and index files. The ingester buffers incoming logs in memory and writes them to the WAL and EFS for durability. Logs are grouped into chunks, and then when the chunks close due to size or time thresholds, they are flashed to EFS along with their corresponding index entries. The BoltDB shipper then uploads both the chunks and index files from EFS to S3 asynchronously. Once chunks are safely written to EFS, the WAL entries for that data are cleared. This ensures durability through EFS and long-term storage in S3, even if Loki restarts or crashes. The pros of this setup is that it's cheaper due to S3 for larger than a few gigabytes volumes. And now that the EFS is not a durable storage, we use it as a safety net, basically in case of an ungraceful shutdown. The cons are that the index files can get very big and slow queries. It requires a bit more complex setup than just using EFS. And again, we have no structured metadata support. We can use it for small to medium workloads, up to a few hundred gigabytes per month, if we don't mind about the slower queries when it scales. And finally, the last option, and the one that is the most current, and the one that I would prefer that you use, is the TSDB, is the time series database basically with EFS and S3, the version 13 storage schema. Logs arrive in the ingester, they are buffered in memory. At the same time, logs are written into the WAL on EFS for crash recovery. When size or time thresholds are reached, Loki flashes chunks and writes them into TSDB blocks stored on EFS. These are partial TSDB blocks, by the way. Then TSDB shipper uploads blocks from EFS to S3, and once this upload succeeds, local EFS copies can be cleaned up. For the WAL, once the flash to S3 succeeds, the WAL entries that correspond to this block are removed. Now, if Loki crashes during upload, a partial block on EFS can be retried after restart. This is where EFS protects against ungraceful shutdown. If you query all logs, Loki fetches blocks from S3. It can cast them on EFS, so repeat queries are faster. That this solution is scalable. We have faster queries than before, even at very large volumes, especially if we use a compactor. We'll talk about the compactor later. It supports structured metadata that will help us query with querying logs. It's also a version, a storage option that is being actively developed. The cons have to do with a heavier compaction process that requires more resources, but the cost is not that big to be a concern. We can use it for medium to large production workloads, up to terabytes per month. It offers fast queries, structured metadata, and very good scalability. Let's move on. Okay, this is the section where we'll set up our services and run them. We'll prepare them in the right order. We'll start with Loki, then with OpenTelemetry collector, and finally, Grafana. We'll use this sequence because the OpenTelemetry collector is using Loki, so this is why we're starting with Loki. Okay, this is a Docker file. We don't have to change anything. It needs this loki-config.yaml file that we'll make later in the next slide, basically. If we're using S3 for storage, like in the last section with TSDB, we need to create an S3 bucket and block all public access. Okay, these are the three options that we have. The three config files that we have to support the three storage options that we have for Loki. I strongly recommend to go with the most up-to-date approach, which is the last one, the TSDB with EFS and S3. There's a lot of information in this configuration file, but let's talk about some of the basics to help you familiarize with it. I say that we just describe the configuration file on the right, which is the one, the latest one and the one that we should be using anyway. Auth-enabled false. This has to do with whether we want Loki to work with tenant ID or not. The ingested buffers incoming logs before cutting them into TSDB blocks and flashing them to EFS. The while the write-ahead log, it's stored on EFS at /while, ensures logs aren't lost if Loki crashes before flashing blocks. Flash on shutdown true tells Loki to finish writing all logs that are in memory to EFS before it shuts down. It basically writes the blocks to EFS. When Loki restarts, TSDB shipper checks EFS. If it finds any created but not yet uploaded blocks, it uploads those blocks to S3. Chunk idle period 5 minutes. If no new logs arrive for this stream for 5 minutes, close its current chunk. The stream in Loki is all log entries that share the exact same set of labels as we said earlier, that we can define them to be the environment, the service name, the version, etc. Max chunk age, 1 hour. Force close basically any chunk that has been open for an hour, even if logs are still flowing. So it doesn't remain open forever. The chunk retain period 30 seconds is after cutting a chunk, keep it in memory for 30 more seconds before freeing it. Because sometimes queries come in for recent data that's just been flashed. Keeping it briefly in memory means Loki can answer those without reloading from S3. Then we have the life cycler. Is the component that manages the ingester membership and state in Loki's ring. The membership setup replaces the need for an external database. It uses a gossip protocol, so all Loki nodes can automatically find each other and stay in sync. The ring is just a shared map, hash table that tells each node which data it's responsible for. Log streams to ingesters. what goes where. 7946 is Loki's Go support. Member list is mainly used when Loki runs in microservices mode, but it's still necessary here. Something must back Loki's internal ring data structure. That's why we have it. Now, I'll say something briefly because we're talking about membership regarding the scaling. Horizontal scaling in Loki does not happen by just replicating the same instance multiple times. This is wrong. It will definitely create problems and inconsistencies. The way to horizontal scale and run Loki in microservices mode is to split the roles, the compactor, the ingester, the querier, and scale each one independently. We also have here the replication factor 1. This is basically for high availability. It defines how many ingesters that are ring members each log entry is written to for availability, and that's it. The index rotation, it says that basically a new block is cut every 24 hours. Up to the time that the blocks are partial blocks. Block names are prefixed with a Loki _index version 13. The TSDB shipper says that the active blocks are written to the /index directory. The cache for index lookup is in TSDB-cache. It keeps recently used index metadata locally to reduce S3 reads. Then we have the compactor. It runs in the background to merge small TSDB blocks into larger ones and clean up old blocks. It uses /compactor as its working directory. I don't know if we should keep on going because I see the time. Let's move on. The ruler also can participate in the ring. That's why there's a member list. Let's move on. Okay. Now these are the steps to upload the Docker image to ECR. We install the AWS CLI. This is an example curl command to install it. We don't need necessarily to run the AWS configure list. We run, again, I'm saying that I'm on Mac and this is the way to set environment variables. So we run export for the access key ID, for the secret access key and the region. This will not persist throughout the restarts though. We add then, the next step is to add the Amazon EC2 container registry power user policy to the user used to upload images to ECR, and Amazon ECS full access to work with ECS clusters and services. Then we log in from the command line using this command. Again, we need to replace the ID here, the user ID, the 798 with the one you're using. And we navigate the folder the Docker file exists and run the docker build command and then push. This is the task definition for the Loki service. Again, we use it as is. We upload it to the AWS task definitions. Now we have to create the Loki service based on the task definition that we just uploaded and enable service discovery. This is crucial. We enable the service discovery service. We also add the namespace. And this is the final DNS name that we will use to access Loki from another service in the VPC, like the OpenTelemetry collector and Grafana. We do this basically to avoid any complications regarding load balancers, target groups, etc. As we don't want, with each restart, that ECS Fargate creates a new IP for the Loki service to go on and change this IP to the services that are calling it. I'll move on to the next slide. This is the OpenTelemetry collector Docker file. Again, we use it as it is. It also needs a configuration file. we have a look at it here. Okay, there are two configurations files that I'm sharing. The left one is the one supporting version 11 of the storage schema of Loki. Also, it's the one that's using the endpoint ending in /v1/push for Loki, which is the old way of pushing data from the OpenTelemetry collector to Loki. The new way, which is the right one, and it's also the one supporting Loki's schema, storage schema version 13 with DSDB, uses natively OTLP. So the right one is the one that we're using now. What we need to know for this, the logs are being sent via gRPC from the app to the collector, and from then on, it's HTTP. So let's talk a bit about the content here. It has a memory limiter. It checks memory usage every 1 second. It caps memory at 4,096 megabytes. It allows temporary spikes up to 1,024 megabytes before dropping data. It basically prevents the collector from crashing if it receives too much data. The batch groups log records before exporting, flashes a batch either every 5 seconds or when it hits size limits, sends a batch once it has 1,024 log records. It improves the throughput and reduces exporter load, basically. Now, what we should be careful is that even if we have declared the memory limiter and the batch, if we don't include these in the pipelines at the end, where it says processors, in this array, they won't be taken into account. So this is something that we definitely have to remember. Now, this is the task definition for the OpenTelemetry collector. On the right, we push, like we did with Loki, we push the image, we build the image and push it to the ECR. And we also push this task definition to AWS for the service to use it. Again, we have, during the creation of the service, enable service discovery, as we did with Loki. Finally, excuse me, we see the Docker file for Grafana. Again, we can use it as it is. It also has two environmental variables that I wanted to just mention. The anonymous enabled equals false and the anonymous org role equals admin. The second one, the org role equals admin, means that if you have the anonymous access to Grafana enabled, the user that we log in basically to Grafana anonymously will have the admin role. But this is being overridden by the task definition. So even if you have something wrong here, you can override it with the task definition. Grafana doesn't have a configuration file exactly, but it has this data source YAML file. Here you can see that in the URL, we're using the Loki service discovery service and the namespace that we created earlier. So we can reference it in the same VPC without need to do any more effort to find the IP and register it like this. So if we're still logged into AWS, we go to the directory that the Docker file and the Grafana data source YAML is, and we build our image and push it to ECR. This is the task definition for Grafana. Now, just like we did with Loki and OpenTelemetry collector, we'll create the Grafana service by using task definition. And again, please don't forget to enable the service discovery. From now on, we'll have to go on to the security group inbound rules again and add one more entry. The entry is for port 3000. Again, we leave the source open, 0.0.0.0/0, because we want to access, this is in order to access Grafana from anywhere. These settings, we must be really careful about this. These settings are for development environment to try and test it yourself. It's not for production environment. Normally, Grafana should run in a subdomain with its own certificate. We should split the services that we're using in different security groups, so they only accept requests from one another, etc. So please bear this in mind. And now basically it's time to put what we built to the test and see the end result of our effort. We'll set up a .NET API to use this login system. We'll first update our CS prods with the packages we need to write logs to our login system through the Serilog OpenTelemetry sync. You can see the packages here. Next, excuse me, we set up Serilog as our login provider, and we configure the OpenTelemetry sync in order to send the logs to the OpenTelemetry collector through gRPC. We remove the highlighted write to console because even though we might have wanted to have logs written inside the container, it can be useful many times. If we leave this in our logger, we will send these logs to CloudWatch as well, due to the task definition of the services where there is a log configuration section that we cannot remove. And the thing is that even if we retain the logs in CloudWatch, let's say for a day, there will be still significant charges due to the ingesters. So we must be able to, we must remember to not include this. Also with this setup, we'll be able to inject the iLogger and send our logs to the OpenTelemetry collector. Now we see a screenshot from Grafana. This is an example of a really simple log. Basically, it's the logs running in loop. You can see the counter, it's 999. But this is where I want to emphasize the fact that we have used structured logging, but the reason Loki is able to display it like this, and we can filter using this structured field, is because we're using the TSDB version 13 of storage for Loki. If we were using anything else, or even if we were using this and we're using an older version, the left-hand side version, let's say, of the OpenTelemetry collector, we still won't be able to do this.
Hi, Stathis.
Yeah.
Excuse me for interrupting. Sorry, we're running a little low on time. I don't know if you've got just a few slides left.
I'm almost done. I have, I think, two more slides.
That's fantastic. Sorry to interrupt. I'll let you carry on.
Yeah, thank you, Matt. Okay, let's have a brief look at traces and metrics. So, for a full observability suite, we need traces and metrics. We use traces because we want to have correlation of operations under the same transaction. They provide end-to-end request paths across microservices. So logs can have a different structure on its service of a distributed system. So it's not that like they're always consistent. I mean, different teams may be handling each service. Traces include spans, which, unlike logs, have a duration and keep their structure across services. In a trace, which basically is a process, such as the creation of a user, each span shows an operation, includes a hierarchy, and belongs to a trace. This way, we have the correlation under the trace. For example, we have an HTTP post request to the /user endpoint. This is a top-level operation triggered by a client request. This will have child spans. This was the root span. The child spans can be the validation of the request payload. The check if the user exists, which is also caused by the same request. The user service.create, which is another call to the service, is a downstream service call inside the request handling. So all these are child spans. Now, before we use the term instrumentation, we need to know what it is. It's adding code or libraries to your application to produce logs, traces, and metrics in a standard format such as the OTLP. There are three well-known examples in .NET. The OpenTelemetry instrumentation SPNet core that creates spans for every incoming HTTP request automatically. The OpenTelemetry instrumentation HTTP that creates spans for outgoing HTTP calls. And the OpenTelemetry instrumentation SQL client that creates spans for SQL queries. Now, by adding the right package and configuring OpenTelemetry in our .NET app, many spans are recorded automatically without changing the business code. So if we want to use a custom span, in .NET, the activity is a span. So we can use a command like start activity with whatever name we like. And as long as we use the start activity inside the request that already has a trace, the span will automatically be contained in the correct trace. If we start an activity outside of a trace context, for example, in a background worker with no incoming requests, it will create a new trace instead. We can also use baggage to add more metadata to our traces. We can use tags to add more information onto our spans. Generally, the context propagation is something that it's worth reading about. But the context propagation happens automatically for HTTP or gRPC. For messaging, for example, if we're using RabbitMQ for our communication of our microservices, we have to create the context propagator ourselves, which is a header basically in the channel properties. And finally, a brief introduction to metrics, why we want to have metrics. There are numeric measurements that can be aggregated over time, such as counters. They answer questions like what was the average response time of an endpoint, how many errors occurred in the last day for this API, or even how many resources, for example, users were created. By using OpenTelemetry for metrics, we can have the service, the environment, and the version of each measurement, so we can more easily link them to our logs and traces. Here is an example of how we can include traces and metrics in our .NET API. And once this setup is in place, we can use Jaeger or Tempo, even better, for traces, and Prometheus for metrics. So they're not logs, so they need their own, let's say, service like the logs need Loki. So it's Tempo for traces, Prometheus for metrics. Jaeger is also very well known. More configuration changes will be required in the OpenTelemetry collector config, in the task definition, and Grafana to properly expose and visualize both traces and metrics. The Jaeger traces are also visible through Jaeger's own UI and can be viewed in Grafana as well, but Grafana's Tempo has a better integration with Grafana and supports S3 for persistence natively, so this is a big plus. Now with Prometheus, I don't know if you would like to store the metrics. Probably you can't push the metrics to when persisted to S3 directly. You have to use a backend before, like Thanos. Or you can use another service like Alert Manager to send alerts without storing them. And yeah, something final is that Jaeger needs to write to Elasticsearch. So I would go with Tempo for sure. That's it. I don't know if there is time for any questions. Sorry, I did as fast as I could.
Sorry, no problem. Thank you. Thanks for that. There's a lot of information going on there. There's a lot of really good actionable advice as well. The slides have got a lot of detail on them. I wonder if you could share those with the viewers.
Sure, yeah, of course.
Brilliant, thanks. If you can share a link with us, we'll put it in the chat and we'll put it in the notes for the video as well.
Okay, yeah, sure.
Brilliant, thank you. Thank you very much for that. I think we will just move swiftly on to our final session. I just want to say thank you very much for a great session with a whole lot of, as I say, really useful information.
Thank you for having me. Thank you. Bye.